So welcome everybody. My name's Gavin Chadbourn. I'm your MC for today on the seminar on crack detection in concrete pipes using deep learning assisted computer vision. Something I'm quite interested in. As I said, my name's Gavin Chadbourn. I work on my own, or have my own little company called Optima Asset Advisory that specialises in durability, materials, technology, and asset management, predominantly working with clients in the transport, infrastructure, and water sectors. We've got two great speakers today. And I'll introduce them in due course. Two presentations. The project is a project on use of AI in the monitoring of water pipes. So water authorities use CCTV technology to monitor reinforced concrete pipes cracking. The technology has its drawbacks, and it can lead to asset owners spending unnecessary money on repairing or replacing or relining in service pipes that are still performing to standard. So the researchers in this project from University of Technology Sydney have partnered with the Concrete Pipes Association of Australasia to develop a better way of monitoring and measuring pipe cracks. They're developing deep learning assisted computer vision that will have far greater resolution than current CCTV detectors and collect more accurate data on crack widths. The innovation will help asset owners make more informed and cost-effective decisions about which pipes need repairs. Researchers will also gather data on acceptable crack width limitations, always a contentious topic that, under diverse environmental conditions. This data will then go towards a revised and more precise Australian standard. So our first speaker is Karen Thompson. Karen is the Executive Director of the Concrete Pipe Association of Australasia, which represents the manufacturers of reinforced concrete pipes, box culverts and associated products in Australia and New Zealand. Karen graduated from the University of Queensland as a civil engineer with extensive experience in pipe and precast industry in both Australia and overseas, including the design, supply, manufacture, installation, marketing and business management of civil precast concrete and a range of pipe materials, including plastic, vitrified clay and steel. Please welcome Karen, and I see you've got your presentation up, Karen. I can see that nice and clearly, so the IT's working.
I was a bit eager. Oh, hi, everyone. My presentation is, I'm leaving the technical side to Yancheng, but what I wanted to do was to set the scene on, what our CRC partnership is with UTS and SmartCrete. So the CPAA really values this partnership that we've entered into between UTS and SmartCrete. It's got the potential for a breakthrough in methodologies and improved specification and verification. The project is a perfect example of an attempt to solve industry-identified problems through industry-led, outcome-focused, collaborative partnership between industry and UTS as the research organisation. We're aiming to develop a technology which will enable improved condition assessment and data analytics of installed concrete drainage pipelines, as well as supporting standards development. So I guess what the challenge is that currently the industry relies very heavily on CCTV for the inspection of newly installed concrete drainage pipes and routine maintenance inspections as well. It's very widely used and it underpins most of condition assessments. But the reality is the technology has a key limitation. It simply doesn't have the resolution needed to accurately measure fine cracks, particularly anything below 1 millimetre. And I'll explain to you soon why that matters. CCTV operators, they identify defects such as cracks, and they estimate the crack width based on experience or past entries into software. Repair, maintenance and replacement decisions are made on this somewhat imperfect data. We're relying on a tool that isn't designed for the level of precision that is actually being reported. The consequence of the limitation is that the crack widths tend to be overestimated in practice. I hope you can see here that what I've highlighted is that, that they're actually saying that they've measured a crack width of 1 millimetre, but then they qualify it with it's too fine to be measured. But they record it as a defect of a crack width of 1 millimetre, which means pull out and replace, basically. So we have instances like that happening all the time. The reporting can lead directly to decisions to line, repair, or even replace that are still structurally sound and perfectly capable of performing as intended pipes. From an installer's and an assets owner's perspective, this translates into unnecessary expenditure, disruption, and inefficient allocation of finances. It just isn't a technical issue, it has real financial and operational implications across the industry. Despite the lack of technical capability for CCTV cameras to measure crack width accurately below 1 millimetre, there's many incidences of CCTV reports stating crack width measurement down to the 3rd decimal place. Reporting cracks with widths to this accuracy portrays a level of accuracy for what is essentially an estimation of a crack width. A level of accuracy to 1,000th of a millimetre is simply not possible with current camera technology. Yet installation contractors are forced to either undertake remediation or spend time and money to undertake further analysis of such reported defects based on this misleading reporting. I guess I've got to build the scenario of why it matters. It's a really high cost, and we estimate it, and we think it's a conservative estimate to be around $400 million per year. And that's based on just, you building a scenario which is there's 566 council areas in Australia. We assume that each council area, on average, has a number of relines and a number of fiberglass patches, which are done like in localised sections of pipe, and it adds up to about $400 million per annum. So there's a lot at stake. We also have a gap in our standards. AS-NZS 4058, it's the standard for the manufacture of concrete pipe. It's a performance-based standard. So to verify a pipe as a strength class, the manufacturers perform routine testing of strength on equipment which is shown in the picture. The strength is verified by a given load being applied with a crack of up to a maximum specified value occurring under the load under controlled conditions. The crack width nominated is simply a quality assurance performance indicator. It's not a value that is intended to be the maximum allowable crack width in the field, but it often gets adopted as such. The allowable crack width varies with increasing cover to steel. CCTV reports do not correlate cover to steel, nor do the reports include the design cover for the pipe. So what is normally assumed is always that the lowest crack width applies to every pipe. In the factory, the crack width and depth is measured by a feeler gauge, as you can see from the picture on the left. The use of the feeler gauge for factory load testing is very common throughout the world for concrete pipe manufacturing standards as a quality assurance method. If the cover to steel is 20 mils, the 0.2 mil feeler gauge is used and the tip must not penetrate a crack more than 3 mils deep, and that's how we measure it. Just to give you a sense of allowable crack width, I mean, a $5 note is, oh, don't quote me, I think it's 0.126 millimetres, so it's less than 0.15. When we were doing some factory testing of some old exhumed pipes, I tried to stick a $5 note into a crack and could only just get it in there, and this pipe was ultimately load tested. But it just gives you a sense of the size of allowable cracks. We're all familiar with hairline cracks. They're visible, but they are not measurable. They're expected in all proof load tested concrete drainage pipes. They're also expected in all installed concrete drainage pipes where applied load approaches pipe design load. There are specifications that do not allow the existence of hairline cracks in installed concrete pipe. They have a no crack policy, which just doesn't make sense with a steel reinforced concrete structure. But these specifications make no steps to ensure that loads applied are less than what would see the steel doing its work and hairline cracking occurring. So I think I'm trying to paint a little bit of a problem our industry has. The other thing is crack assessment can differ. Crack assessment varies by the operator and what the operator sees, the camera that's utilised, the equipment, the distance the camera ends up being from the wall of the pipe, the level of zoom that's applied with the camera, and even if they have to clip, the spec says they have to clean the pipeline, and they clean the pipeline through pressure cleaning, the walls are very, very wet, and so every little hairline crack looks like a canyon. You can see from these pictures, this is just the same image, just with 3 different zooms. So if you saw the top image, you'd go, yeah, maybe there's this very, very small hairline crack. When you get down to the zoom on the bottom right, that is disaster, and it would be pulled out. But the reality is the pipe has a very acceptable crack width. And that's just one of the issues we get from the CCTV reports. So what we're hoping for is accurate field crack measurement being possible. That's our dream. And that's where Yancheng and his team at UTS offered up the idea that deep learning assisted computer vision could be a game-changing alternative to current CCTV monitoring of installed pipes. And then asset owners need to have an improved understanding of the mechanism of cracking in concrete pipes. The crack initiation and propagation needs to be better understood, and how it differs from ordinary concrete due to the low water cement ratios in the product, the level of compaction that's utilised in the process of manufacture of the pipes, and the very small diameter of steel that's incorporated compared to normal steel reinforced structures. And the effect the pipe shape has on crack propagation, and the importance the underground environment has on the corrosion process. Not all cracks are what they're cracked up to be. So in steps Anu Castell and his research team at UTS, who are undeniably capable of researching the issue and providing data to better specify allowable for performance in given environments. So stream 1 of the research project is to develop a deep learning assisted computer vision as an alternative to current CCTV monitoring of recently installed and in-service pipes. The technology will be able to achieve 0.1 millimetre. We're not looking for that 1,000th of a millimetre that is currently reported, because that's not possible, but 0.1 will actually do the job immensely better. The development and commercialisation of equipment, process and inspection guidelines related to this new technology would provide the asset owner with appropriate data to make improved, informed assessments and reduce unnecessary costs in construction. And then comes in the supporting research. Autogenous healing is an important phenomenon in installed concrete pipe. Autogenous concrete self-healing reduces the crack width or can totally seal the crack if the crack width is small enough. This project is investigating the relationship between crack width, self-healing process, and the corrosion of reinforcement of concrete pipes. Other supporting research it's covering is that the corrosion behaviour of steel in concrete pipes is unique. It suggests that corrosion products forming quickly at the crack tip create a barrier at the steel surface, limiting access for oxygen and humidity to the sound steel. As a result, active steel corrosion stops. In this case, oxides formation does not lead to any additional concrete cracking, as there is enough room for the rust expansion within the crack. Moreover, the loss of mass required to heal the crack tip is marginal. As a result, the early corrosion does not affect the service life of the structure. Research on exhumed concrete pipes in the past has showed that there was no significant corrosion after 50 years in service. This project seeks to further consolidate on the past research by investigating the corrosion of reinforcement in concrete pipes in aggressive environments that stormwater pipes may be subject to. And assessing the environmental, like where the pipe is. Pipes are buried structures, and so it's in a completely different environment underground to most concrete structures. And so the environment that the pipes are in is important. So our key insights that we're trying to uncover is that cracks can self-heal and will communicate how and when. Small cracks do not equal a durability failure, and we want that to be clear. And we want to also just show the research to show that the current approach can somewhat be too conservative for concrete pipes. The research outcomes are going to have great industry impact. Firstly, by improving the quantification of cracks and when they are actionable defects, will reduce the instance of unnecessary repair. The useful life of concrete pipes is a value that determines depreciation expense of asset owners. This research can show how CCTV inspection data can be used to increase the useful life using the knowledge of cracks healing and not propagating as real justification. The ability to measure, not pretend to measure, or errantly estimate crack width will underpin improved decision making. So our outcomes are going to be a new inspection technology, the new improved updated standards that provide asset owners with more confidence in the performance of the product, and cost savings from not replacing or repairing unnecessarily. That's it. Thank you. Over to Yancheng to tell you the whole technical details.
Thank you, Karen. I think that was a very good overview of the challenges that you have with accurately and reliably measuring cracks, but more importantly, how do you interpret what those cracks mean in terms of corrosion risk. So our next speaker is Yancheng Li. He is a researcher at the School of Civil and Environmental Engineering at UTS. His research focuses on applying computer vision, deep learning, robotics, and large language and vision language models to improve the inspection, monitoring, maintenance, and decision-making of concrete infrastructure. His work aims to bridge advanced AI techniques with practical engineering applications to enable more efficient and reliable infrastructure management. Dr. Li is widely published and has over 170 journal and conference papers to his name. Over to you, Yancheng.
Thank you, Gavin. Thank you, Karen, for laying out very clear, background information on why this research is very necessary. So I'm probably gonna skip some introduction slides, but let me start going. So first, of course, as Karen mentioned, this is a part of the SmartCrete CRC project. We are just 1 year into the project, so have made some progresses over here. So before formally going to the slides, we just maybe briefly introduce our team, which we are using, AI, computer vision, and agentic vision to for all sort of concrete defect detection, quantification, evaluation. We also use large language model to offer professional advice for following assessment, also decision making. So that's our thing for our research team. So content, I'm gonna skip some background introduction over here. Probably straight dive to the key technology we have, which is deep learning computer vision for pipeline crack and pipe crack assessment. Let's skip over here and come to here. So current solution, since we are only 1 year into the project, so our main focus is still in the quality insurance process, which is during the testing. So in this practice, basically what people do is, as Karen mentioned, you insert a feeler gauge into this crack to see how much it is, and try to, based on personal experience, to professional experience, to have the evaluation on the pipe. The thing is, the crack is probably going to go through the pipe longitudinally, so for 2.4 meters or 3 meters. So it's not that easy to evaluate entire crack using human eyes to do that. Then talk to the current computer vision with deep learning. You all know probably there are lots of research in the field already published using deep learning for crack detection, crack quantification, etc. But the key challenge here is for crack, as Karen mentioned, there's a need to detect very thin crack or to quantify this very thin crack up to 0.1, which is very challenging. There are limited success reported for thin crack quantification in controlled environment, but we are doing things on the field. So that's why we propose this new approach with robotics, with edge computing, with computer vision, try to see if this is going to work. So this is the main framework of our algorithm. So we're basically using multimodality framework for the high precision and pipe crack detection and quantification. In terms of multimodality, so we are using two inputs, which is first one, as normally do for deep learning crack detection, is RGB data. So that is the image we normally have with our phone, with camera. The other modality is the depth information. The depth information refers to the depth from the camera to the concrete surface. And they will produce a similar image as the RGB image, but which each pixel as the distance from the camera to the concrete surface. So you have a whole level of map of the depth. The reason we introduced this one because for crack detection normally it's easy. You use RGB image, but your output or your measurement is the crack length, crack width in pixel. We have to convert this pixel measurement into physical measurement. So typically people do is to put a reference object on the side, so beside this crack. So this is not doable actually if you want to do it very, very quickly. So introducing this depth map, going to remove the need of reference object on site. And with this one, we also introduce the super resolution technique over here in this algorithm with the aim to really zoom into detail of the pixel. And we are able to detect this crack as narrow as 0.1, even less than 0.1 millimeter for the width. Okay, so what we do here, we use data collection. We use the RealSense from Intel RGBD camera. So this camera gonna collect image, give you two type of files, which is first one RGB, the second one is the depth. So you can have all these images all together. So we also bought a robot, so we modify them. Basically, we install a RGBD camera in the front. So install this camera in the front. So in a sense, we're gonna collect this over here, this RGBD camera. So we're gonna pull out the data to our laptop. We're gonna measure process the image we have. So worth to notify over here is this one still the post-processing, but I'm gonna show you very soon. We are developing this real-time assessment as well. This is specs for the camera for RGB and depth. So they are not very high in the resolution. It's only about 2K, and the depth is only 1K. So we have to increase the resolution of the depth image. So the overall framework over here is we basically using two pipelines, which is the depth image and the RGB image. We go into different stage of feature extraction, also feature fusion together. Try to combine them together. The thing here is why we use depth maps. The depth maps, as mentioned before, is first to provide reference for quantification. So we need something, which distance from the camera to the crack surface as the reference measurement for quantification. Second one, we're going to remove the background noise because for many pipe cracks, you have a water stain, you have many things. You also have sometimes some plants. So these steps, based on the depth feature, you can observe the feature change. For example, the sudden depth increase which indicating, okay, there may be some crack happening. So you're going to be able to remove all the other, image noises or disturbance, so make the measurements more accurately. So this is a process for crack quantification. We are able to first make the skeleton of the crack, so the middle line over here. Then based on this skeleton, we can measure the crack length and crack width. We're using the small circle, inscribed circle method to measure the crack width over here. So this is a setting we did in, I think, Blacktown over there. So in the Holcim factory, the setting including, of course, this is the loading facility to load up this concrete pipe. So while the load is holding, we send this robot into the pipe to collect the image. So going through all the cracks, and the data will pass to the our laptop. We collect all the data. So over here we have an example of RGB and depth images. So you can hear RGB image here with very fine crack, very thin crack, sometimes nearly invisible. In the depth is more look like messy in a way, because it's more like color map. So we have to analyze those two input to get the feature of the crack, try to locate the crack among those all the vast pixel of other type of concrete background, and try to get the feature of the crack because it's very thin. So we tested over 15 type of pipes with different diameter, and they collect over 4,000 images pairs of the concrete pipe on site. So for the algorithm validation, of course, we did two steps. First one is zero shot, because we also did some other research on the other type of concrete defect. Typically, that defect is very, concrete crack is wider, not as thin as 0.1 or 0.15 or 0.3. It's probably in terms of millimeter level. So we try to test if only training using that data set, which is not anything related to the concrete or not anything related to the thin crack, try to see how it's working. And then we use fine tuning, which basically we're going to use this 4,000, part of the 4,000, maybe only 25% of the 4,000 images. Try to reinforcement learning to make sure this refinement, to be able to have a better result. So that's the two steps we did. So this is the result we have. This is the RGB image. This is depth image. This is a typical, you have a pipe, you have some painting, says what type of pipe, whether it's qualified or not. So this is like concrete with uneven surface, with some surface texture, and which create, some disturbance for the depth image. And we also have other type of very thin crack over here. So for our zero shot, we are able to somehow get a, good result. But you can see the color difference on the label on the crack. The green one is true positive, which means, okay, if all the crack are green one, like this one is perfect. So we have false negative. The thing you don't really want is, a TN, true negative. So as you can see from the zero shot, we have a certain level of success in terms of, quantify the crack. Also label the crack, quantify the crack. Maybe somehow it's a bit over exaggerating this crack width over here. So this is not something we want. So we fine tuning the algorithm. We are able to, really nail down the crack length. I'll show you the stats very soon. We also select different scenarios. We also intentionally put some plantation, some grass over here. Try to, create disturbance. We also put some water somewhere. I don't think we show the water mark over here. But you can see from all these scenarios, we are able to detect the crack quite successfully over here. Sorry for, because it's very thin crack, you can't really see much. But I give you some data you can see very clearly. So evaluation metrics, we have 4 metrics to, investigate whether this, algorithm is working fine. So higher value means better. So the highest value is 100. So for all those parameters, we have improved significantly from zero shot to after fine tuning. So the thing very important is MROU, which indicating the identification on the pixel level on the crack is 85, which is very good so far. So we are also compare with each individual crack. So we have over here the ground truth, which is dashed line, which is the real depth width of the crack along the length of the crack over time over the length. So the pred, which means the prediction old, which means the zero shot prediction. You can see there is quite a variation with the ground truth, but the fine-tuning result is very close in matching the result over here. And this pattern appears to all the scenarios over here, so which we can confidently say, okay, our result has been very good. Then I'm going to show to you quantitatively how good it is. So we try to find the minimum crack width, because along the long crack there are some points which have narrow crack. That's why maybe it's 0.1 or less than 0.1. So we have the 3 columns, which is ground truth, the real number you should identify, and fine-tuning and zero shot. You can see with zero shot is quite exaggerating of the crack width. And this one, from 0.18 you recognize as 0.7 millimeter. From 0. Somehow undermine the crack width from 0.08 to 0.03. So which means the algorithm wasn't able with zero shot, wasn't able to really correctly define the cracked pixel in the image. But with fine-tuning, we are able to really reduce the error, and from the very high, nearly 300% to 20% to nearly 10%, it's a very good result in terms of minimum crack width. So as very important parameter is 0.1, as mentioned from Karen. We are able to detect this very fine crack over here with our algorithms. This max crack width, which is along the cracks where we have the widest crack over here. So you can see our result also pretty good in terms of the error over here, in terms of the absolute error, in terms of relative error in the percentage. So we are quite okay in a sense. We are also able to detect the crack length, measure the crack length based on what we have in the image. So similar pattern showing over here. We are able to really measure the crack with our algorithm. Imagine it's not like you have to measure one by one. Once you have this algorithm trained, you simply input image, then this algorithm is able to tell you the crack width, crack length, etc. We are also able to detect crack depth, but of course it's not the aims for this project, so I didn't really show over here. So I'm also going to show you, remember what we have in the previous slides, we're using the robots only to collect image. We are not able to process in real time online over there. But now we have some new development with edge computing. We have the robot over here, those few robots. We install RGB camera, not that high quality. We can upgrade into very high quality RGB camera. We also have the control, the system control the robot, going forward, going backwards. We also have this onboard chip, Raspberry Pi, to run the algorithm. This simple demo, of course, is initial development. It's not that accurate yet. Shows you the potential of our system. You can run through the using the robot to go through the concrete sample. Over here, the green text shows you the result right away. Tells you the length, the crack width, the average width, etc. So once you scan through the object, such as pipes, such as concrete structure, you can have the result and analyzed and stored somewhere for later decision making. So that's something we did for this over here. And conclusion, of course, we use some RGB camera and also some multimodality deep learning algorithm to really quantify the ultra-thin crack in a pipe. And we also have AI-powered robotic system for concrete pipe crack quantification And this system is able to quantify thin crack, roughly 0.1, even lower, with high accuracy. And worth noting this one, we have the potential to extend into other type of concrete defects. We are doing this one as well. So including corrosion, including other type of discoloration and spalling, etc. We will also be able to do it. And other ongoing work, we are using large language framework to capitalize the crack quantification for further risk analysis, structure assessment, because only the measurement doesn't mean it's only the starting point. We need to know the reliability of the structure. We also have a multi-agent system to streamline crack quantification with maintenance schedule. We also developing the deployable edge computing agentic vision to have real-time assessment and also integrate with professional advice or domain expertise for following decision-making process. Thank you. That's all from me.
Thank you, Yancheng, and thank you, Karen, once again. Two very good presentations there. I'll open the floor to questions. You can either raise your hand and just ask the question, or if you're feeling a bit shy, you can type it into the chat and I'll read it out. It looks like we've actually got one question come up. So let me just see. Donovan, looks like you. Can you introduce yourself, Donovan, and fire away with your question? You're on mute, Donovan.
I'm Donovan Marnie. I work with a consulting group called Pipeline Condition Assessment. We focus mainly on corrosion, but we do plastic as well. The questions that I have about this research is that it doesn't. I think the research can be really targeted much better rather than keep it broad. And I'd like to see it focus on critical pipelines rather than all pipelines, because I'm sure we need to think about the consequences of failure in the various pipelines. So we don't need it everywhere. So that means we can allocate the spend accordingly. And the other thing is, it's like there's a missing factor around the material behavior, which is the concrete behavior, which is the underlying driving mechanism for the failure. So I understand this is a visual tool. What's to stop me from taking a few photographs, chucking it into a ChatGPT or Claude or whatever, and ask it to tell me what's going on? So that's a fear. I don't think it might not be reasonable, but that's a fear. And the other one is, if we can articulate the consequences of failure, we can then think about the probability of failure and think about the assessment in a slightly different way. And that may help help CIA better target its resources, and you guys target the research questions, because I don't think it's all going to fail through mechanical failure. I think there's internal, whether it be corrosion. And by the way, I think we can replace steel with glass as well. I think there's composites you can use for reinforcement. Steel industry won't like it, but I think there's alternatives there. But you know, there are ways to deal with the material chemistry that I'm not sure we're taking care of, and there are ways to deal with the reinforcement. And I'd love to see a probability of failure, which then works out useful, from which you can derive useful estimation of useful life. That's all my little ramblings in my notes. Thank you.
Karen, do you want to go first? Or
Yeah. Thanks, Donovan. I think we're not really getting to the point of failure here. The biggest issue is when a pipe is newly installed, it's subject to these CCTV inspections, and you've just got very small cracks, and it's nowhere near the ultimate load failure crack that you're going to get. So that's why we're not interested, I guess, in the failure mechanism. We're in that upfront acceptance, just as the pipe is starting along its working life, so to speak, and it has cracks that are visible to the eye, and they're being estimated to be wider than what would actually be accepted to just for an asset owner to say, yep, okay, I accept those pipes and they're going to last 100 years. In actual fact, the cracks are not normally of a width that are of great concern. If they are of a width of great concern, the Concrete Pipe Association and its members are the first to say, do something about them, because, you know, our underlying belief is that a concrete stormwater pipe, we're talking about, that's what 98% of the concrete pipes in Australia are supplied to do, should last at least 100 years. And it's already been demonstrated that that's what they do in a stormwater environment. Unlike sewer pipe, most concrete sewer pipes that are installed at the moment, they're only, I mean, I remember in my younger days, most of them were only designed for a 30, 35, 50-year life at absolute max, but rarely 50-year life, because that's not what an asset owner wanted to pay for. So there'd be a sacrificial layer put on the inside of the pipe, and it was known that as the pipe got to its design life, that sacrificial layer would start to deplete. And so there's the difference there.
Thanks, Karen. I appreciate the context very much.
Yeah, I want to follow up with Karen's answer. Sorry. Thank you, Donovan, for your question. I think very, very insightful. Of course, we are not feeding the result directly into a large language model. We are doing something. You're spot on. So Karen explained the point, which is the main focus for this project. But as researcher, we are thinking something beyond this project. So we think about how we can utilize this crack detection result, feed into the front element modeling, feed into the pin modeling, try to plus the live load, service load of the pipe, to think about how this pipe is going to propagate, what's the risk behind it, and what's the reliability of the assessment on this one. So you're spot on. We are actually doing this one as well. Yeah.
I would like to see a comment. I would like to see some materials consideration, because you are working with material after all, and I'm sure it's another group of a team working in that space. But it's nice to see a model that thinks about both the visual. Look, I did this work over a decade ago with John Mashford at Cyro, so I think Voot's aware of the work we did there. But we try to think of the material as well, and its chemistry, and its behavior, and its deterioration or durability over time. Thank you. I've said my piece.
I think Harish Srivastava was next.
I think thanks, Yancheng, and you can hear me?
Yep.
Yeah, thanks, Yancheng and Karen, for nice presentation. I think it's a really good technology you're trying to develop. But there are a few comments I would like to offer, probably that needs to be addressed. When I see the robot movement, it pretty much, because it's a crawling robot, it will pick up the pictures from the floor. In factory condition, you may rotate the pipe and map it, but in field condition, everything is fixed. Unless you move to 360-degree image acquisition, you can't sort of get that image, or get the full sort of perspective of pipe. And second thing, you did mention that you have put some dirt and grass in this thing, but I guess need to take your robot to actually install pipe and see whether that kind of dirt is addressed by your sort of robotic system, because in factory where you trial, this is very, very clean condition, but after transportation and actual installation in place, is not exactly the same condition. So I think it's a good start, but I think it needs to take few more things into account before even you can say new pipe mapping is successful, and then probably lifetime assessment is another thing, because CCTV is normally used during the life or the periodic inspection, but that time the condition is very, very bad, and even most of the robots are not able to work in the stormwater pipe because of the blockage, and also because of the the water, residual water there. So it's a good start, but I think we need to do a fair bit more before it becomes a practical handy technology. Thank you.
Thank you, Harish. Good to see you. Yes, I value your comment. As I mentioned, this is only the beginning part of the project. We're only doing the quality insurance for the new production pipe at this stage. Of course, we are keen to move into the next stage, which is, really test our algorithm, see the complication in a real environment. I do recognize, there's a lot of many challenges over there, with very, messy, surrounding environment. Sometimes crack may not be there visible or something else. So the challenge for us here is we can't really see many data, which is controlled by some agencies, so we can't really access the data yet. But if there's a possibility, we can look into the problem. I'm sure we can find a solution to do it, including, for example, using other sorts of modality of data to see the hidden cracks as well. Yeah, happy to discuss further. Yeah.
Thanks.
We've got a few questions in the chat that I'll read out. So one for Yancheng. It says from Subic, are there any public data sets to work around or any synthetic data generation methods?
Yes or no. So most of the data is for the normal concrete, which is very ideal concrete crack image. So for specialized pipe images, they are limited. You may find some, but in terms of zooming to this very thin crack quantification, there's probably none of this data set available yet. So that's the first question. Second question, in terms of can you create some data set by some new technology? Yes, we can. And of course, this has to build on with existing data set. So you can, for example, you have 100 images, you 100 data set, you can augment into 1,000 or even 2,000 with some pattern, but still need some, further investigation on whether it's possible, to do that.
Yeah.
But you still have the original data, as a beginning.
Yeah. Actually, there's I've noticed on the attendance list, there's quite a few people attending from local governments and water authorities as well. So they may have data sets that might be of interest to you. So you could, maybe reach out to Yancheng afterwards. Another question from Jacinta O'Connor. What diameter pipes is the technology suitable for? Is the pipe required to be offline, i.e. no flow through the pipe? And would the technology be suitable for sewer as well as stormwater? Yancheng, do you want to answer that one maybe?
Yeah, we tested the diameter from I think 375 millimeter to nearly 1.5 meter. So many different type of, we're gonna give you probably updating with Karen, like for different diameter of pipe, what's the quantification, accuracy for this one. But in terms of going to the sewer or stormwater, this is some stormwater pipe. Maybe Karen, the best person to answer this question.
Yeah, this technology, what we're doing is this research is really focused on stormwater, and that's where, the large percentage of concrete pipe is newly installed these days. So that's why that is, and it's the issue is around pipe that has just been installed and hasn't yet been taken over by local government or a road authority, like a state authority as their asset. It's very newly installed where the major problems are with acceptance. So at this stage, I wouldn't think that it would be suitable for sewer, because for sewer, you're looking at defects that are very, very different to the defects that you would expect in a newly laid concrete stormwater pipe. We think it could be used to, like if you install a concrete pipe and you say, okay, it's got a 0.15 millimeter crack. Well, a year after you install it, you could use the technology to go back and see, because you've assumed that the crack is stabilised, and you could go back and check that assumption, whether it's stabilised or whether it's autogenously healed. And prior to that happening, I mean, most of the times when the CCTV cameras are sent down, the pipelines are newly cleaned. So, yeah, it's most suited for stormwater.
Got a question from Sammy Jang.
Hi, I'm Sammy from Melbourne Water. I just had a couple questions. Firstly, ironically, I do work in sewer, but also in drainage as well. So first question is, a lot of the images are for circular drains. With Melbourne Water, we have a lot of large 2 to 3 meter square culverts and different drain shapes. So does the technology able to meet those weird shapes? And also, is the end goal to have this as a kind of a camera attached, or is it purely software? Because currently we have like a crawler, it's got a camera head on it. Is it going to be auxiliary to that, or is it going to be just software?
Okay, so first question in terms of the shape of the pipe. So circular shape or square shape, I think all can do it, but of course the quantification process is different because you have to consider geometry to convert this, all this one into the real measurement. So their geometry is different. So it's doable, of course, for different type of pipes. Second one is, I think to adopting, let's say think long way game, to adopting such technology, it's not only the software. But probably also need upgrading this camera as well. But of course, we have to think about practically, we can using existing camera to do the measurement, because we do know the distance from the camera to the roughly to the surface. We can have some estimation, but we can work with different scenarios. Ideally, would be like you upgrading this camera, because we do require this one has distance measurement, very precise measurement, so that we can convert into the real physical dimension. But everything's possible, yeah.
Xiang Chen. Got another question, Quang Danuyan.
Sorry, can
Still
you hear
there,
me?
Quang? Yes, we can now.
Thank you, Dr. Yancheng and Karen, for the very interesting presentation. My name is Quang Yu. I'm from TechnoCreek, and our company is working specialized in doing assessment, structural inspection and assessment, and many of them I have chance to inspect many assets like concrete pipe, concrete covers, and I'm very impressed with the technique. Then we can measure the crack width, which really matter regarding rectification methods, repair, crack repair, something. But during the presentation, one of my major concerns regarding the data that you use for fine tuning, it looked like, based on what I saw, the background condition of the data. So the data you collect is like from the asset is recently installed, right? As Karen mentioned. So, but actually in the real scenario, imagine you inspect a structure like after 5 years, after 10 years, or even 20 years, the condition, the surface condition is much different from what you collect from this data. So the thing here is the problem right here is regarding the domain shift. When you training the model with the data you collect at this time and apply to the real scenario, I saw the accuracy is quite impressive. Like F1 score is more than 28%. So it's really impressive. But if you have you tried to apply on the data sets that you collect from real scenario from the asset, like 20 years after 20 years from the first I mean the condition survey, I think is really significant different from what you are training, and I think the results would be decreased significantly, I suppose. So in this case, what will you do to address the generalization because I guess that you train the model using supervised methods. So in order to increase the generalization, one of the methods is you have to collect as many as data you have, as many as image. However, it have many constraints to get a large scale of data and increase the generalization of the model. So do you have any, this is the first step is very impressive, but it still have a long journey from a very good result here until to deploy the model and apply to the real scenario in the near future.
Yeah.
So do you have any solution for that?
Thank you for your comment. I think I have to emphasize first, it's only for that quality insurance. It's newly produced pipe. We're not yet into the used pipe yet, simply because we don't have the data. So to answer your question is, for any scenario, I think we need to retrain the model. For example, if you think about this pipe, sewage pipe with long time service, we have to get access to the data first to be able to let the AI know, okay, we are dealing with a new problem, not with the previous one. That's why you see the process we have is we use a fine-tuning or transfer learning for this one. Basically, the previous algorithm is trained on the very ideal data for concrete flat surface and not on the pipe. We don't have the crack with very thin crack in the image yet. We try to test where it's possible. Then we later fine-tuning with existing data set, try to do that. So that's the process. Same logic will apply to the new practical condition. For example, use any in-service pipe scenario. We're gonna have to sample the data first. Try to let this AI knows, okay, we are dealing with something new. You have to work around it. So that's the general answer for your question.
I think we're just wrapping up, but we've got one more question. Arnaud has been waiting quite patiently. So our last question from Arnaud Castel, please.
Thank you. I will be quick. So I'm Arnaud Castel. I'm UTS, and I'm also part of this project, working with Yancheng and Karen. And I just would like to comment on Heinrich, comment on the complexity of field condition, which is true. But Karen, please let me know if I'm wrong. But currently, the current CCTV technology is using a robot to investigate pipes. So I think it will be quite straightforward to swap the existing poor quality camera to the new high performance camera developed by Yancheng Li and just do exactly the same thing. So whatever is possible to do now could be immediately possible to do with the new technology without any further barriers. But maybe I'm wrong. I'm just a thought.
That's the dream, but it's small steps first. And we're not at that point. Yancheng's chaining the model. He's been to factories. He has pipes from factories back at the university. They are able to move their cameras through real pipes with real cracks, etc. And the next step is to take it out into an installed stormwater line and test it out. So I think it will be possible, but it's just, one step at a time.
Yeah, I agree. I mean, as soon as the training is complete and Yancheng is happy with the way of managing all the field, possible field, interference, that should be practically possible. Beliefs. Thank you. That's all.
You and the team will be very busy. There's a lot of interest in expanding this technology to in-field assessment of older operating pipes. So looks like you'll be on this project for years to come, Yancheng. Look, thank you, Yancheng and Karen, for your very informative presentations. I think there's a lot of questions there. There were a few more in the chat that we didn't get to. look, I'm sure people will reach out to you directly and you can respond to those questions there. As Natalie said, the presentation, or this presentation, this seminar will be made available, the recording. But thank you again to both of you, very informative, and we'll wrap it up there. Thank you.
Thank you. Thanks everybody for attending.
Thank you, everybody. I'm going to answer the
Bye.
question in the chat.